No. Nelle lomba canale quei te.
No.
Also these plants. That's down here. I know that place. That's my rock.
Okay, so we talk about slope stability and also construction of road embankment is another very important engineering, how to say, construction. Actually, it's more happened in construction road, construction railway, and construction foundation. Okay, so most of those happens in road embankment. So in road embankment, actually, based on the traffic, we usually design the load, right? Design the embankment. We want to compact it. We want to make it steep enough that to hold such a traffic, right? And this is why we compact the soil, because as long as it's steep, the sediment is less, and the shear stress is very strong. Soil is become very strong. So based on some code, you have a designation. You need to reach some density. You need to reach some compaction degree. But how much you should to reach? You need to analyze this based on soil properties. Most is physical properties. And after the compaction, under such a density, under such a compaction degree, you need to analyze how much sediment will happen. Does it reach the limit of the code or not? So this is the construction of road embankment. And also construction foundation ditch. So if you want to build a whole building, unless to process the foundation soil, we need to make a foundation to hold the building. This pile foundation is the most foundation we use, especially in the soft ground, in Wenzhou district or in Shanghai. Those places are all near to sea, and the ground is very soft. Ground soil is very soft. Pile foundation can reach a very deep ground and strengthen the foundation. So this is a foundation ditch. Those are piles. So you need to understand the soil property in here and how much piles and how dense of the pile. What's the distance between those piles should be designed. Those are all related to soil mechanics. Okay, so everything is that first you need to understand the ground you process. The ground is about soil. And then let's say the development of soil mechanics. We go this part very quick. The development of soil mechanics have 4 phases. The first is pre-classical and classical soil mechanics, phase 1 and phase 2, and then modern soil mechanics, the latest 100 years. Prior to the pre-classical phase, for example, these 2 buildings, actually people already understand how to do a very big construction, but soil mechanics is not a branch of science at that time. Those buildings is just based on the experience, right? People based on self-experience, they know that if you build the pyramid like such a shape, it will be much stable than a round or any other shape. So it's just based on experience. And in here, the Leaning Tower of Pisa, why it's leaning? Because people based the experience to build the tower. They don't know how to process the foundation. You know that the tower of the Pisa, the foundation soil is soft soil. It's soft soil, soft soil. So if you didn't process the foundation soil very well, of course, it will have a differential settlement. For example, the settlement in this side is less than in this side, so it will have a leaning. This is why this happens, because people have no conscious on process foundation. At that time, most of the construction is only based on experience. But after that, the pre-classical period of soil mechanics, after those construction, people understand that they need to do something to the soil. So in this period, concentrate on the study related to nature slope and unit weight of various types of soil, as well as the semi-empirical earth pressure theory. The natural slope of soil when tipped in a heap were first studied for formulating the design procedure of retaining walls by this guy, and also some other proposed some semi-empirical equations or some other series. And in the classical soil mechanics, the first phase, we have Coulomb. Coulomb is a very big scientist in soil mechanics. Later we will learn Coulomb series, Coulomb shear strength, in shear strength part of soil mechanics. This guy used the principle of calculus to determine the true position of the slide surface, then to analyze the stability of slope. In soil, we had the retaining wall, use the law of friction and cohesion for solid bodies. Up to now, we still use friction and cohesion for soil to analyze the shear strength of soil. And Coulomb theory was used by many others to study cases such as inclined backfills supporting the charge and determine the magnitude of lateral earthquake. This is Coulomb. And in the phase 2 of classical soil mechanics, people getting started to learn the coefficient of mobility. And this guy is also a very big scientist. He developed the theory of stress distribution, because before you learn the settlement, you learn the shear strength of soil. You need to know the stress, right? In soil mechanics, as long as you want to calculate the shear failure, you need to know the stress, shear stress, right? Right, the minor stress, the major stress, and what is the net stress, those stuff. So stress distribution actually is the first step to analyze this problem. This guy develops the theory of stress distribution under load varying areas, homogeneous, semi-infinite, elastic, and isotropic media. We will learn this in chapter 10. And Arterburg defines the clay science friction as a percentage by weight of particles smaller than 2 micron in size. And later, this guy defines the plastic limit and liquid limit for soil. Liquid limit and plastic limit is the two main properties to define soil. If the soil is a clay or sand or silt, so in most cases it depends on the plasticity of soil, that is liquid limit and plastic limit. And finally, we go to Tessage. Tessage developed the theory of consolidation for clay as we know today. So now we still use the theory of consolidation. The theory of consolidation is developed from the saturated soil to calculate the settlement of foundation. And after that, after the consolidation theory of Tessage, then people developed to unsaturated soil. But all of the theory is based on Tessage consolidation theory. So he is also known as the father of modern soil mechanics. He is a very, very, very big scientist in soil mechanics. This is Tessage. He's already died. Oh, what's the shame? You can't see me. geotechnic engineering after 1927. So people already consensus the soil mechanics and know that it is a very important science branch. So they start to hold some conference to discuss some engineering problem together. So up to now, if you want to attend, as long as you study for master, you will notice that every year there are a lot of conference of something like a symposium everywhere all over the world to talk about geotechnical problem, talk about the development of civil engineering, anything, a lot of things. And by the early 1970s, computer added finite difference and finite element solutions were applied to various types of geotechnical engineering problems. So actually now, not only for master, but also for many other research doctors or professors. Some of the professors even never stayed in the experiment laboratory, but they still study civil engineering, geotechnical engineering, only based on computer. Because now you know that we can mold. For example, I can build a model for this building, analyze its stability under different load. For example, I give a very huge wind load. For example, because we in Wenzhou sometimes we have big wind, heavy wind, right? For example, the earthquake, if it is still stable, we can check this, right? But to check this, those stuff, for example, the frame, the structural frame, or the foundation, they follow different theory. Those doctors, those professors, what they start with computer, they just to try to mold the soil or the structural stability more, how to say, more reliable actually. They build those equations, they build this series into computer code and makes the analysis is more reliable. This is what they do. But another part is the laboratory stuff. So if you do research later, actually people do three different things. One is doing stuff with computer. Some part of them doing laboratory work, and some other researchers they're doing practice work, right? For example, designation, maybe designation, something like this. But computer, yes, it helps a lot in geotechnical engineering because the geotechnical engineering problem is very huge. It's very huge. You can't only doing laboratory work based on very small sample to analyze a very big stuff, right? And then there are some other development in geotechnical engineering. And we say end of the era is the last of the early giants of the professor, Peck. Peck is a guy that analyzed the settlement of the soil upon a tunnel. And he passed away at 2008 at the age of 95. Wow. So after that, we say that this is the end of the era because Peck is a people in the same period with Tesach. So after him, we think that all the previous science they are all dead, and we need to start a new page, something like this. Let me say it's the end of the era. And this is the development of the soil mechanics. Actually, you see that people soil mechanics is a new science branch, much newer than chemical, physical, than those stuff, than the material, than metal, than all those stuff, right? So we give a quick brief of the first chapter. And from the second chapter, we start to learn the physical properties of soil. And the second chapter, at the very beginning, let's see how soil comes from, the origin of the soil and grain size. Origin of the soil, you just need to know how it comes from. Yes, it comes from rock. And then grain size distribution is